A question regarding string instance uniqueness in Python. I was trying to figure out which integers Python only instantiates once, -6 to 256 it seems, and in the process stumbled on some string behavior I can't see the pattern in. Sometimes, equal strings created in different ways share the same id, sometimes not. This code. Prints. I don't even see the pattern, save for the fact that the first four don't have an explicit function call, but surely that can't be it, since the plus in C for example implies a function call to add. I especially don't understand why C and G are different, seeing as that implies that the ids of the components of the addition are more important than the outcome. So, what is the special treatment that AD undergo, making them come out as the same instance?
In terms of language specification, any compliant Python compiler and runtime is fully allowed, for any instance of an immutable type, to make a new instance or find an existing instance of the same type that's equal to the required value and use a new reference to that same instance. This means it's always incorrect to use is or by id comparison among immutables, and any minor release may tweak or change strategy in this matter to enhance optimization. In terms of implementations, the trade-off are pretty clear. Trying to reuse an existing instance may mean time spent, perhaps wasted, trying to find such an instance, but if the attempt succeeds then some memory is saved, as well as the time to allocate and later free the memory bits needed to hold a new instance. How to solve those implementation trade-offs is not entirely obvious. If you can identify heuristics that indicate that finding a suitable existing instance is likely in the search, even if it fails, will be fast, then you may want to attempt the search and reuse when the heuristic suggested, but skip it otherwise. In your observations you seem to have found a particular .release implementation that performs a modicum of peephole optimization when that's entirely safe, fast, and simple, so the assignments A to D all boil down to exactly the same as A, but E to F don't, as they involve named functions or methods that the optimizer's authors may reasonably have considered not 100% safe to assume semantics for, and low ROI if that was done, so they're not peephole optimized. Thus, A to D reusing the same instance boils down to A and B doing so, as C and D get peephole optimized to exactly the same construct. That reuse, in turn, clearly suggests compiler tactics/optimizer heuristics whereby identical literal constants of an immutable type in the same function's local namespace are collapsed to references to just one instance in the functions .func_code.co_consts. To use current Python's terminology for attributes of functions and code objects, reasonable tactics and heuristics, as reuse of the same immutable constant literal within one function are somewhat frequent, and the price is only paid once, at compile time, while the advantage is accrued many times, every time the function runs, maybe within loops etc. etc. It so happens that these specific tactics and heuristics, given their clearly positive trade-offs, have been pervasive in all recent versions of Python, and, I believe, IronPython, Python, and PyPy as well. This is a somewhat worthy and interesting RF study if you're planning to write compilers, runtime environments, peephole optimizers, etc., for Python itself or similar languages. I guess that deep study of the internals, ideally of many different correct implementations, of course, so as not to fixate on the quirks of a specific one. Good thing Python currently enjoys at least 4 separate production-worthy implementations, not to mention several versions of each, can also help, indirectly, make one a better Python programmer, but it's particularly important to focus on what's guaranteed by the language itself, which is somewhat less than what you'll find in common among separate implementations, because the parts that just happen to be in common right now, without being required to be so by the language specs, may perfectly well change under you at the next point release of one or another implementation and, if your production code was mistakenly relying on such details, that might cause nasty surprises. Plus, it's hardly ever necessary, or even particularly helpful, to rely on such variable implementation details rather than on language-mandated behavior, unless you're coding something like an optimizer, debugger, profiler, or the like, of course.
Python is allowed to inline string constants. A, B, C, D are actually the same literals. If Python sees a constant expression, it treats it as a constant. str is actually a class, so str whatever is calling this class constructor, which should yield a fresh object. This explains E, F, G. Note that each of these has separate identity. As for H, I am not sure, but I'd go for explanation that this expression is too complicated for Python to figure out. It's actually a constant, so it computes a new string.
An answer to s.lot's suggestion of examining the bytecode. Yields. So it would seem that indeed the compiler understands AD to mean the same thing, and so it saves memory by only generating it once, as suggested by Alex, Mache and Greg. Added case I seems to just be str realizing it's trying to make a string from a string, and just passing it through. Thanks everyone, that's a lot clearer now.
I believe short strings that can be evaluated at compile time will be interned automatically. In the last examples, the result can't be evaluated at compile time because str or join might be redefined.